Good afternoon, students. So, few more students needed to join in this GATE class. So, today we are discussing in geotechnical engineering. So, this is a very important topic. More number of questions are from this subject. So, also the same syllabus, the same content, the same procedure you can use in competitive examinations like AE examination, JE examination, SSC examinations, everything. Okay, already we discussed the introduction about the classes, everything. So convey the message to your friends and log in this class properly. Okay, only few students only available. Make a call to your friend. Okay, and today's session, engineer Bilal sir. So he is working in SRM University. So sir will take today first session only sir will take. The next week one more session sir will have. Okay, so do you have any queries, any doubts? Means directly you can ask with Bilal sir. Okay, um, thank you, Bilal sir. Bilal
Sir,
sir.
yes, sir. Thank you, sir.
Ah,
Thank you,
yes
sir.
sir.
Thank you, sir.
Yes
I
sir.
will continue, sir.
Okay sir, you can carry on sir. Yes sir.
Okay. Okay. Good afternoon, everyone. I hope you all are doing good. So, myself, Mohammed Bilal. I'm currently working in a SRM group of institutions. So, I'm going to handle the subject of geotechnical engineering. Especially, this session is going to be full and full focused for GATE exam. Okay. As Sir already mentioned, there is a very important topic as far as competitive exams are concerned. A major chunk of the questions in the question paper will come from this particular area, geotechnical engineering area. So, so for a better clarity, I'm just showing the year-wise split up, okay, of different subjects, how the questions are split up in different areas. Uh, for the last past 8 or 9 years, you can see it. So in geotechnical engineering, minimum we can expect around on an average we can expect around 15% of the total marks or total questions will come from this particular area. This not only applies for GATE exam or any other competitive exams concerned. This is going to be the case. Okay. So the major part or the major more number of questions are going to be taken from this particular area, geotechnical engineering field. Okay. So it's a very important area, you can say, right? So, so first of all, geotechnical engineering, what are the subjects comes under this particular umbrella means? So in general, geotechnical engineering, it includes soil mechanics, rock mechanics, soil engineering, rock engineering, and all. Okay, but if you look into the syllabus, GATE syllabus or any competitive exam syllabus, geotechnical engineering, in academic point of view, it comprises of the two papers, soil mechanics and foundation engineering. Okay, so these two subjects are included in this particular area, geotechnical engineering area. But in general, the term geotechnical engineering, it includes all soil mechanics, rock mechanics, soil engineering, rock engineering, and all. Okay, subjects like that. But for a syllabus academic point of view or exam point of view, we can take this two areas. One is soil mechanics, and the another one is foundation engineering. Okay, right. So let's get into the topic. So this class we are going to deal on the soil mechanics related topics, and the next subsequent sessions we can get into foundation engineering also. Okay, so for your clarity, you can just look at the table for a moment, then we can move. So every year, minimum there will be around 13 to 14% of the questions will be from this particular area, geotechnical engineering area. You can see that clearly in the um, slide. Okay. You can see that clearly here. Okay. Right. So in geotechnical engineering, the major percentage of the questions are going to be from this area. Right. Let's get into the topic. So first, we are going to deal with the soil mechanics area. Okay. So why this particular subject or the particular material is a difficult one to deal with. Not only the subject, even the material soil is a very difficult one to deal in a field also. Okay, so I think you people are all in final years, so we can say directly the one of the toughest or one among the toughest subjects in civil engineering field will be the soil mechanics paper. Okay, so it is basically because of the material we are dealing with that particular paper, the soil material. It is a complicated one. That is the main reason why we are feeling we got a vague feeling when we deal with that subject. That is the reason. Okay, so just a short intro about the nature of the material. Okay, so why it is difficult to deal with, why we are facing complications in analysis area also, or in analyzing the particular material. It is not as easy as dealing with the fluid or dealing with the solid that we do in solid mechanics or standard materials, and in fluid mechanics and hydraulic engineering. This particular soil mechanics subject, as well as the soil material, it is a typical one, and it is a complicated one to deal with. These are the reasons for that. The first one being the stress strain relationship for a soil deposit. It is in a non-linear fashion. It is in a non-linear fashion. So that is the first complication it creates, that material creates. Okay. So if we look into the other material, if we take a solid material or steel material for instance, the up to the elastic limit, we can see a linear relationship between the stress and strain. But for soil, it is not the case. So in the first place, it is creating a difficulty for us in that way. Okay. Hence, the difficulty in using easily determinable parameters to describe its behavior. Okay. The second one will be the soil deposits have a memory of stress. Okay, so it has a stress memory. Okay, so this particular point or this particular phenomenon of the soil, it will create impact during the consolidation stage. Okay, the consolidation process of the soil. So in that particular area, we will see that in the next next few slides, the consolidation topic or consolidation property of a soil. So the consolidation of the soil is mainly affected by the consolidation property of the soil is mainly affected by this stress memory behavior of this material. Okay, their behavior is vastly influenced by the stress, time, and environment, or other factors which may alter their behavior. So, for instance, if you see a pre-consolidated or over-consolidated soil will settle less when compared with a normally consolidated soil. Okay, so pre-consolidated soil will settle less when compared with a normally consolidated soil. So in that instance, this stress memory is going to play a major role there. Okay, so we'll see about that in detail the latest slides. The third point or third nature of the soil will be it is not a homogeneous material. Okay, it is a highly heterogeneous material. Okay, the soil deposit being far from homogeneous exhibit properties which vary from location. So when we are talking about location, not only in the depth wise, okay, in lateral directions also, the layers or the properties or the type of soil will vary. Okay, so point to point it will vary. Okay, so since it is a naturally formed material, it will not be in a homogeneous state. Okay, right. So that is the reason. So that will create some problem for us. And the next one will be we can't directly see or visually examine the soil in all the times. At a few instances, we can directly examine the soil. Okay, so other than that, the soil layers are buried and hidden from the view. So visual examination of the material is not possible. Okay, so one has to rely on tests carried out on small samples that can be taken. Okay, so the problem in this particular situation is we can't guarantee that the soil parameters truly represents the field conditions. Okay, so during sampling stage or during the transportation stage or during the preservance stage of the sample, their properties may change. Okay, so there is no guarantee, right, that our sample will replicate the same state in the field. Okay, so that is one of the problem. And then taking sample from the soil is a very tedious task. So most of the time we will get an undisturbed sample. I'm sorry. Most of the time, we will get a disturbed sample. So collecting an undisturbed sample from the soil is very, very difficult one. In fact, we can say it is an impossible situation. But for a theoretical purpose, we can say theoretically we can say it is an impossible situation. But for practical considerations, few types of soil we can name it as undisturbed samples. Okay, there are a few specialized equipments like piston sampler or a thin walled sampler. For instance, we can say we can get a truly undisturbed sample using those samplers. But most of the time, the samples we collect from this field, the soil samples we collect from the field, they are in a disturbed nature. Okay, right. So in soil which is sensitive to disturbance, the behavior submerged from the laboratory test may not reflect the likely behavior of the field stratum or conditions. Okay, right. So the first topic, the very important topic as far as the questions or academic point of view or competitive exams is concerned, it is the phase relationship topic. Okay, we can definitely expect one or two questions from this particular area, phase relationship area. If you got notes, you can make note of this next few equations. Next equations, the equations we are going to discuss in the next few slides. Then please take a note of it. It will be helpful for the discussion during the discussion time, where we will discuss a few problems based on these equations. So all these equations you could have studied during your fourth semester. I think you two have got the soil mechanics paper during the fourth semester. I think. Let's see that these equations you could have studied already, but let's take it as a recall session. Please make note down of this equations, phase relationships. So we are going to discuss around 10 or 15 relationships in this particular topic. Okay, right. And we can expect at least one or two questions from this particular area. Okay, phase relationship. So what we are going to see in this particular topic means, so as I already said, soil is a very different material. It is, we can't say it is particularly comes under a solid category or it particularly falls under a fluid category. Okay, so it got all three phases of matter. It got solid particles, solid grains, it got liquid in the state of water, and it got void spaces filled with the air. Okay, so a soil mass got all these three states of matter in it. Okay, so that is the reason we can't apply the particular apply the laws which is suitable only for solid materials, or we can't apply the laws which are suitable only for fluids. We have to make use of the laws of both solid and fluids to discuss a soil material, a soil mass. Okay, so this is a three-phase diagram of a soil system. So it got solid part, and it got water part, and it got air. Okay, so in a few cases the water may be replaced with the oil. Okay, but majority of the time it will be water. In some areas like oil fields, the water part may be replaced with the oil. Okay, right. Okay, okay. So we are dividing the total soil mass into these three particular portions: solid portion, liquid portion, and air portion, and we are representing their respective weights and volume in this manner. So for instance, the total weight of the soil is contributed from these three different states present in the soil mass. So the first one will be solids, and it will be represented by Ws. The next major material is going to be water, and it is represented by Ww. And the third one is air, and it is represented as Wa. But for calculation purpose, we won't consider the weight of air. Okay, and usually we neglect it and we take 0 for the weight of air. Please make a note of it. So more in calculation, we take this weight of air as 0. Okay, right. And similarly, we are going to divide the volume, the total volume of the soil mass, into three areas. Okay, so three portions. The first one will be the solid portion, and its volume is represented by capital Vs. And the second portion, it is going to be the volume of the water portion, capital Vw. And the third one, it is going to be the volume of the air part, Va. So in this instance, we have to take the volume of air into consideration. We should not neglect it, just like we did with the when we were talking about the weight. During weight, we can ignore the weight of the air, since it is going to be in very feeble quantity. We can ignore that. But when it comes to volume, we should not ignore the volume of air. Okay, so in some types of soil, say for example, if you take shale. Okay, if you take shale, or if you take a very coarse grained soil, the volume of air, okay, the volume occupied by the air space, it will be very high. Okay, so we should not ignore the volume of air. Okay, but when it comes to weight or mass, we can take the weight or the mass of air as 0. But for volume, we should not do that. Please keep that in mind. Okay, so we are splitting the total weight into Ws, Ww, and Wa for solids, water, and air respectively. And in same manner, we are splitting the volume, total volume, into three areas: volume of solids, volume of water, and volume of air. And in this volume area, the volume of water and the volume of air. So in other words, the water and the air, it is going to occupy the void spaces created by the solid grains. Okay, so the soil mass, how it formed means it contains numerous sediments in it. Okay, so in grain states, so the grains create gaps between them. Okay, void spaces between them, and the void spaces, it is going to be occupied by either water or air. Okay, so we can collectively call this volume of water and volume of air as volume of voids, VV. So here VV is equal to VW plus VA. Okay, right. So from this diagram, we have to extract some. We are going to extract a few mathematical equations. So that's why I'm taking a bit time here. So please register this figure into your mind. So how we are splitting the soil mass into three different components. Okay, so please keep that in mind. So next, the relationships we are going to derive from that phase diagram, three-phase diagram. Okay, so the first relationship will be water content or moisture content. Both are same. So before getting into this topic, getting into deep in this topic, I have to remind you people a very important thing. When it comes to soil mechanics, a single property can have many different names. Please keep that in mind. Okay, so for instance, you could memorize this particular formula as water content in your memory, but when we face the question paper, they could have asked what is calculate the moisture content of the given sample, like that. Okay, at that moment, you have to keep that in mind. Both water content and moisture content is same. Okay, please remember that. Okay, so this is a very important point I have to give you before starting this getting into this equations area, because one single property can have many names as far as soil mechanics is concerned. So please keep that in mind. So for water content, the another name is moisture content. Okay, so please keep that in mind. So what is it? So water content, it is represented by the letter small w. Okay, we are not using capital W here. The reason being, we have already allotted the capital W letter for the total weight of the soil. You can see that in this particular slide, in the particular diagram. So we have already used the capital W for total, for representing the total weight of the mass. So we should not repeat that again for our some other quantity. Okay, so for that reason, we are expressing the water content or moisture content with the letter small w. Okay, lowercase w. Okay, so it is defined as the ratio between weight of water and the weight of solids. So in numerator, we are having the weight of water, and in denominator, we are having the weight of solids. Okay, so we can calculate this particular water content or moisture content using the mass quantities also. Okay, similar to weight, we can calculate the particular property using the mass also. We can say it as the ratio of mass of water to the mass of solids. Okay, so this is the mathematical formula for it. So small w, that is water content or moisture content, is equal to WW, capital W, small suffix W. It denotes the weight of water, divided by WS. It denotes the weight of solids into 100%. So we can from this we can say we are going to express the water content in percentage. Okay, please keep that in mind. So water content is usually expressed in percentage, but when it is used in calculations, the fraction alternative of that water content has to be used. Okay, right. So if it is say for instance the water content is 25%, means we have to use 0.25 in our calculations. Okay, you should not put 25 as it is. Okay, please keep that in mind. So you can express the water content as small w is equal to WW divided by WS into 100%, or using the mass quantities like this, MW divided by MS into 100%. So here MW and MS represents the mass of water and the mass of solids respectively. So what is the difference between weight and mass? I hope you people already know it. So weight, it is a force quantity. Okay, so it will be expressed in newtons. Okay, so weight, it will be expressed in newtons. So please keep that in mind. I hope you already know weight. Just I am recalling that. So mass, it is represented in kg units,
kg.
that is grams, kilograms, like that. Okay, right. So weight, it is represented in Newton, so it is a force quantity, but mass, it is represented in kgs or grams. So please keep that in mind. So the when we discuss the different properties in soil mechanics, one more important thing we have to deal is the range of that particular property. So how much the answer, or how much the number we will get from that particular property. Okay, have to we need to know that also, because you can expect questions from the range also. Okay, so they will give the what they can ask, what is the range of water content for a typical soil mass, they can ask like that, and they will give options like it will be between 0 to 100, it will be less than 0, it will be more than 0, I'm sorry, more than 100, it will be equal to 50%, like that, and so on. Okay, they will give options like that. So we have to remember the ranges also, but my advice is, please don't memorize these ranges. Okay, so you can easily estimate the range from the formula itself. Okay, with a few physical thinking about that particular property, and using this formula, we can easily calculate the range of that particular property. Okay, how? Let's see. So for instance, water content. So what will be the answer for water content? In general, they gave us a problem, and they are asking water content for the particular soil mass. We have to find it. So range denotes from what to what the answer may come. That is called as a range. Okay. So water content, for water content property, what will be the range? We can easily calculate from the. We can easily find out that from the equation itself. So how we have to calculate the range means, put 0 on the numerator. Okay, so small w is equal to ww divided by ws. We have to check like this. So minimum will be, how we have to check the range means, so for minimum, you have to think if there is any possibility that the particular quantity can turn out to be 0. You have to check that. So in this particular case, we have to check weight of water. It can be, can it be 0 at any instance? You have to check, think about that. Okay, so if it is 0, what will we get? If you put 0 in the numerator, ww, instead for ww, if you substitute 0, we will get the answer as 0. But you have to think, if it is possible in any situation, it is possible, can it be possible at any situation the weight of water can be 0? You have to think about that. But theoretically, if you speak, for a woven dried soil, if we dry a wet soil in a hot air oven for 24 hours, here maintaining the temperature more than 105 degrees Celsius, or more than 100 degrees Celsius, we can remove all the water present in the white space. Okay, so at that, if we take the dry mass out, we can say this particular soil mass has no water in it. We can put the weight of water as 0. You can say that. So in that case, the water content, small w, it will give the value as 0 for a pure dry soil. Okay, clean dry soil or woven dried soil, the weight of water will be 0, and hence the water content, small w, will become 0. We can say that. But if we go a bit deeper into the soil particle, for the formation of a single soil grain, there are very there are some structural bonds between different minerals. In a single soil grain, there are many minerals present in it, and there is some bonds happened between those minerals, and because of that, we are getting that single grain. So during that bonding, there may be some structural water present in it in a single grain. Okay, so in that case, we cannot, we can say we cannot remove the entire water from the soil mass. Even after oven drying, we cannot remove the entire we haven't removed the entire water present in the soil mass. So in that case, the numerator WW will not become 0, and hence the lower limit will not be 0. It has to be more than 0. We have to say like that. Then we have to check the upper limit. For upper limit, how we have to check the range? We are talking about the range. So range means it will have a lower value from this to this. The range of the particular property, it will be from 0 to 100. It will be 0 to 25. It will be 0 to 1, 0.5 to 1, like that. That is called as a range. For checking the lower limit, we have to substitute. We have to check if we can substitute 0 in that numerator. For calculation of water content, we cannot substitute 0, because even after over drying, there will be a presence of water in the form of structural bond, okay, between the minerals present in a single grain. So we cannot put WW as 0. Okay, right. So this is the method of finding the lower limit. So we have found out that the water content, it cannot be 0. It can be more than 0. We have found come to the conclusion that it cannot be equal to 0, but it can be more than 0. Now let's move on to the upper limit. How we have to check the upper limit means very simple. Check whether the numerator and the denominator will be equal or not at any instance. Okay, at some point, if it is, if it is any possibility that the numerator and the denominator will be same. So one second. Sorry, I'm sorry, got a phone call. Okay, let's. Okay. So for upper limit, we have to check whether the numerator, it can be equal to the denominator at any point. We have to check that. So in this particular case, we have to check whether WW, it can be equal to WS or not. We have to check that first. Okay. So it means if we take 1 kilogram of soil, at some point we have to check, can it can it is any possible, can there be any possible that the weight of water, it will be equal to half kg. It will take half kg from the weight of the soil mass, and the remaining half kg, it will be taken from the solids. We have to check that it is possible. Okay, it is a possible scenario. Okay, so for a fully soaked up soil, there are chances that the weight of water, it can be equal to the weight of soil. So this particular case is possible. Okay, so we are now coming to the conclusion that the water content, it can be equal to 100% also. Okay, we shouldn't stop right here. We have to check the next extreme possibility also. So what it is means, we have to check whether WW, it will be greater than WS or not. We have to check that also. Means, let's take the same example again. We are taking 1 kg of soil sample. We have to think whether the weight of water, it can be more than 500 grams. We have to check that possibility. It is also possible. Okay, it is also possible. The weight of soil can be more than, sorry, the weight of water can be more than the weight of solids present in the soil also. So this scenario is also possible, right? So from this, we are coming to the conclusion that the water content, it has no upper limit. If this particular situation is not possible, we can conclude that it has an upper limit as 100%, but it is not the case. The weight of water, it can be more than the weight of solid also. This scenario is possible. Okay, so in the situation, we cannot claim this particular number as the upper limit of that property. Okay, so this is the method to find out the lower limit and upper limit of ranges for a particular property. So I'm just recalling again, for checking lower limit, you have to put 0 in the numerator. You have to check whether we can put 0 in the numerator or not, right? So for this particular property, we cannot put weight of water as 0, because even after oven drying, there may be the presence of water in the form of structural bonding. So WW, it cannot be 0 at any point. Okay. So hence, the lower limit of this water content is more than 0. And while we checked the upper limit, we got into conclusion that the weight of water, it can be equal to weight of solids, and in some situations it can be more than weight of solids also. So and hence there is no upper limit for water content. So if you get a question like what is the range of water content, okay, and your answer will be this: W is more than 0. You should not write W is more than or equal to 0. But when you see few textbooks, you can see the range of water content as this particular, like this. W can be equal to 0 also. Okay, in few textbooks, they have mentioned that water content can be equal to 0 also. Okay, right. That is also that can also be taken into consideration. Okay, they have not gone much deep into the bonding of the soil grains, and hence they have given that water content can be equal to 0 also. For completely dry soil, water content is 0. They have come to the conclusion like that. Okay, so hence they have written like this: W is greater than or equal to 0. They have written like this. Okay. Okay. So now you can get you may get a confusion like which answer I should answer, which option I should answer in the exam. See, if you got both these options, W greater than 0, and you got the another option as W greater than or equal to 0, the preference should be given to this particular one. The priority should be given to this particular one. Water content is greater than 0. The priority, you should give priority to this one. If you don't have any option like this, W greater than 0, and you got only this option, W greater than or equal to 0, then you can go for this option. Okay, right? So please keep that in mind. Only with this particular property we are having this difficulty. Other properties we know the range in a clear-cut manner, but only for this water content property we will get this debatable range options. Okay, but let's move to the next property. So the next property will be void ratio. Okay, so void ratio, it is represented by the letter E, small letter E. Again, we are not using the uppercase E, capital letter E here. The reason being, we have already designated the capital letter E for modulus of elasticity or Young's modulus. Okay, so during the settlement calculations or subgrade reaction calculations, we use the term modulus of elasticity term. We use that in soil mechanics also, and hence we should not use that here. So for void ratio, we are giving the letter small e. Okay, so it is defined as the ratio of volume of voids to the volume of solids. So it gives the measure of the volume of voids present in a soil. So this is the application of this property. So it gives the measure of the volume of voids present in a soil. So the greater the void ratio, the looser is the soil. So greater the void ratio means there is a presence of more voids in the soil mass, and hence the soil is in a loose state. Okay, right. So it is given by the equation small e is equal to VV divided by Vs. So this is the equation for void ratio. No alternate equations for void ratio, as we saw in water content. It is void ratio have got only one equation. So E is equal to VV by Vs. Again, using the same technique as we did earlier with water content, we can calculate the range for void ratio using the same technique. Now, for lower limit, what I said earlier, we have to check, can we put 0 in the numerator? Okay, so for in this instance, it means, can the volume of voids be 0 in a soil? We have to check it. Is it possible? So if you think about that, it is entirely not possible, because if a soil mass doesn't contain any voids in it, then it is not a soil and all at all. We have to call it as a rock or a solid material. It is not a soil. Okay, if it doesn't contain any voids in it, it is not a soil. It is a rock, or it is simply a solid material. Okay, like steel or concrete, it is just a solid material. Okay, so any soil you take, it will contain a very few amount of voids at least. Okay, so and hence for calculating the lower limit, VB, it cannot be equal to 0. Okay, so now we are coming to the conclusion that the volume of void ratio, the lower limit will not be 0. It has to be more than 0, maybe 0.1, 0.2, 0.3, whatever. Okay, right. Now we are moving to the upper limit. Okay, so for finding the upper limit, what we have to do, we have to check whether the numerator, it can be equal to denominator at any at a instance. Okay, we have to check it. When we are checking volume of voids equal to volume of solids, we have to check whether this situation is possible or not. Okay, I already mentioned one example using the shale rock. It contains a lot of voids in it. Okay, so in that in soils like that, uh, the volume of voids, it can be equal to volume of solids, or it can be more than volume of solids also. Okay, in a very loose soil, for instance, the volume of voids will be much higher than the volume of solids. Okay, so the numerator, it can be equal to the denominator, as well as it can be more than the denominator also. Okay, so for voids ratio, there is no upper limit. Can be okay. So for voids, for giving the representing the range of voids ratio, the lower limit is, it is more than 0. It cannot be 0. It can be more than 0. If we check whether it has any upper limit or not, it doesn't have any upper limit. So voids ratio, the range is E is more than 0. The reason being, VV, it cannot be equal to 0, and hence E is not equal to 0. And the second thing, the upper limit, VV, it can be more than or equal to Vs, the denominator, volume of solids. Okay, and hence void ratio can be more than 1 also. Okay, so we cannot conclude E is from 0 to 1. We cannot write like that. Okay, it can be more than 1 also, right? So this is how you have to find the ranges of different properties. Okay, so in nature, even though individual void sizes are large in coarse grained soils, the void ratios of fine grained soils are generally higher than those of coarse grained soils. See, for example, we are having two soil samples in front of us. So one, it is made up of gravel, for instance. Okay, so one container, it contains the gravel sample, and in another container we got clay soil sample. By visual examination, we can say that the gravel got more voids in it, but if we measure it, we can see the opposite of what we thought. The voids, the total number of voids present, or the volume of voids in the clay soil, it will be much higher than the volume of soil in the coarse grained soil like gravel, as per our example. The reason is, though the sizes of voids in our gravel sample is much higher, but the number of voids in our gravel sample is very, very less. If we take the same volume of two samples, say for example 1 liter of gravel sample and 1 liter of clay sample. Okay, so in 1 liter of gravel sample we may have 50 gravels. Okay, so those 50 gravels, it may create another 50 voids. Okay, so the sizes of 50 voids is higher. Okay, so one size of one void is higher, and it got 50 voids in it in the sample A, gravel sample. In sample B, we got clay soil. Okay, so for same 1 liter, this time we may got 5 million grains, clay grains present in that same 1 liter. Okay, they again create 5 million 5 lakh void spaces. Okay, even though the size of the void is less in clay soil, the number of voids in the clay soil is very much high. Okay, so comparing to the 50 voids present in the 50 big voids present in the gravel sample, here even though the size is small, the numbers is very large in clay sample, and hence the total volume will be total volume of voids will be more in clay soil. Okay, so that is the reason uh, the void ratio of fine grained soil is higher than that of coarse grained soils. So this kind of statements will be useful for you for answering the A or type questions. You know, I hope you know what A or type means: assertion and reasoning type questions. This type of statements will be helpful for that. So please take this into account. The next property will be porosity. Again, another method of calculating the denseness or looseness of a soil. So it is given by the letter small n, because we cannot use capital N because capital N denotes newtons. Okay, so it is a unit. Capital N is a unit, so we cannot use here capital N here. So we are using the letter small n for porosity, and it is defined as the ratio of volume of voids to the total volume of the soil, total volume of the sample. Okay, so mathematically small n is equal to VV divided by capital V. So the difference between void ratio and porosity is, so the difference between void ratio and porosity is, so void ratio, I'm writing the equation here. So void ratio E is equal to VV by VS. But we see porosity, there is no change in the numerator. The numerator remains same, volume of voids. But denominator, now we are not dealing with the volume of solids alone. Now we are dealing with the total volume of the soil. Okay, so please know the difference between the two words. I'm sorry. Please know the difference between the two words: soil and solids. Please know the difference between the two words. So solids means only the solid grains present in the mass. Soil means all three. Okay, solids, water, and liquid. So please know the difference. So here Vs denotes volume of solids alone, but total V denotes Vs plus Vv plus Vw. Oh, sorry, Vs plus Vw plus Va, or Vs plus Vv. Okay, right. So that is the difference. So if you check the porosity range, it is between 0 to 100, excluding those two numbers, 0 and 100. Porosity, it cannot be equal to 0, it cannot be equal to 100 also, but it can be between anywhere between 0 and 100. Okay, please know the difference. If we get an option like the range of porosity, what is the range of porosity? If you get a question like that and you have answers options like this, 0 less than n less than 100, and you got another option like 0 less than or equal to n less than or equal to 100, you have to pick the option carefully, and it is 0 less than n less than 100, because porosity, it can never be equal to 0 and it can never be equal to 100. It will be anywhere between those two numbers. Okay, maybe 0.1 to 99.99, anywhere between that, but it can never be equal to 0 and never be equal to 100. Please keep that in mind. So it is equal. It is usually expressed in percentage, unlike void ratio, which is expressed in decimal, but porosity it is expressed in percentage. So similar, as we already said in the case of water content, for expression we can use the percentage, use in percentage, but when it comes to calculation we have to use the fraction value of the porosity. Okay, so for example, if we get the porosity as 60%, in calculations we have to use 0.6. Okay, so both these properties, void ratio and porosity, express the proportion of volume of voids. Okay, but when it comes to civil engineering, it is more convenient to use void ratio, in which only the numerator VV changes when the volume of the soil changes. Okay, but in porosity, both numerator and the denominator will change. Okay, when the volume of total volume changes, both numerator and denominator will change in case of porosity. But in case of void ratio, it is not the it is not this situation. Only the numerator, volume of voids alone only will change. The denominator, there won't be any change in that. Okay, right. But the term porosity, it will be useful in the field of agricultural engineering. For civil engineering, the convenient parameter will be void ratio to indicate the denseness or looseness of a soil. It will be the convenient parameter. Porosity is not a convenient parameter for our department. Please keep that in mind. The next property will be degree of saturation. So it is given by represented by the letter capital S or S suffix R. Okay, both letters can be used in few textbooks. It is given as capital S, and in some other it is given as capital S suffix R. Okay, so it is defined as the ratio of volume of the water to the volume of voids. Okay, so please understand the difference between void ratio, porosity, and the degree of saturation. So in void ratio and porosity, the numerator is volume of voids. Okay, see here. But in degree of saturation, the numerator is volume of water. So now we are talking about the presence, how much the water is present in the void spaces. Okay, so that is expressed using this particular parameter, degree of saturation. Okay, so the ratio of volume of water to the volume of voids. Okay, so in a soil, if it has say 50% void spaces and 50% of the volume is occupied by the solids, we have to check uh, how much of the void spaces, how much of the 50% void spaces occupied by water, and the rest will be obviously occupied by the air. Okay, right. So that particular thing is expressed using this degree of saturation parameter. So S is equal to VV divided by VW divided by VV. So physical meaning of this is the volume of the voids occupied by water. How much volume of the voids is occupied by water? That is what we are trying to find out using this particular parameter. Okay, right. So VV divided by V into 100, right? So into 100 means degree of saturation is also expressed in percentage. When it comes to calculation, we have to use the fraction format of that. Okay, so now if you check the range of degree of saturation, is there any possibility that, once again, is there any possibility that VW can be equal to 0? We have to check it for the lower limit, minimum range, minimum amount. Okay, so for finding out the range of the degree of saturation, for minimum value, we are checking this volume of water. In can it be 0 at any situation? We have to check it. So for a fully dry soil, okay, for a fully dry soil, the total volume of voids will be occupied by air alone. there won't be presence of any water in the voids. Okay, and hence this situation is possible. VW can be equal to 0, and hence for degree of saturation, the lower limit, it can be equal to 0 also. Okay, so now we are going to check the next extreme, upper limit. Can VW be equal to VV? We have to check this, if this case is possible or not. For a fully saturated soil, full saturation means the entire void is occupied by water alone. Okay, so if the entire void is occupied by water, means what happens? There is no presence of air in the soil mass. Only water and the solids is present in the soil mass. That situation, for a fully saturated soil, this situation is possible. VW can be equal to VV. Okay, now we have to check the next extreme. If VW can be, I'm sorry, I'm calling the mouse. Can VW be more than VV? We have to check this. Then we can come to the conclusion of the maximum limit. Is there any possibility for this? Means it is not possible. The water can occupy only the void space. It cannot occupy the space of the solids. Okay, it can occupy only the void space available between the solid grains. It cannot occupy the space of the soil, solid grain, and expel the solid grain from the mass. It cannot do that. Okay, so volume of water, it can occupy only up to the limit of void space, cannot occupy more than that. Okay, right. So this situation, it is not possible, and hence we are coming to the conclusion that the degree of saturation, it can be equal to 0, it can be equal to 100, and it cannot be more than 100. So we have to write like this, the range of the degree of saturation. So S 0 less than or equal to S less than or equal to 100. So in words, so degree of saturation can be from 0 to 100. Okay, so see the difference in the words. When it comes to porosity, we used the word between. Okay, porosity can be between 0 to 100. But when it comes to degree of saturation, we are using the word from. So degree of saturation can be from 0 to 100. Means both 0 and 100 included. Okay, so these are the, one second. Okay, sorry. Right. So these are the extreme cases. For a dry soil, as we already said, the volume of water is 0. For a completely dry soil, the volume of water is 0, and hence degree of saturation can be 0. Okay. For a fully saturated soil, the next extreme case. Okay. The volume of water, it can be equal to volume of voids, and hence S can be equal to 1 or 100. Okay. Tell in numerals or fraction means we have to say as 1. When we are expressing in percentage, it is 100%. Okay, so for a partially saturated soil means it contains both air and water in its void space. Okay, so that is called as a partially saturated soil. So for a partially saturated soil, S lies between anywhere between 0 and 100. Okay, so these are the 3 cases as far as the degree of saturation is concerned. So please keep that in mind. So next parameter, air content and percentage air voids. So the next material, this is here we are going to deal with the next material that is going to occupy the void space. In degree of saturation, we dealt with the water, and here we are going to deal with the air. Okay, so air content is defined as the ratio of volume of air to the volume of voids, similar to degree of saturation. So similar in degree of saturation, the numerator is volume of water, and here the numerator is volume of air. That is the only change. Okay, so air content is represented using the letters A suffix C, small letter A suffix C, okay, not capital A, because for capital A we will be using for area, representing area. So we are using small letter A here. Okay, so AC is equal to VA divided by VB. Okay, so this is the formula. And another parameter, like just like void ratio and porosity, here we have two parameters for the presence of air, for representing the presence of air. So the next parameter is percentage air voids, NA. Okay, so the change is just like in void ratio and porosity, we saw E is equal to VV VS, and porosity we saw VV suffix, VV denominator total volume. Similarly, here you can see for air content, the denominator is volume of voids, and in percentage air voids, the denominator is total volume. Okay, these are the formulas for air content and percentage air voids, denotes the presence of air in the soil sample. Okay, in two different ways. Okay, so in first case, we are dealing only how much the void space is occupied by air. In second case, we are dealing in the total volume, how much is occupied by air. Okay, so that is the difference. The next are weight quantities. So far we dealt with the volumetric relations. So every property we got volume. Okay, volume related parameters. And hereafter we are going to deal with the weight parameters. So the first one is bulk unit weight or bulk density. So here comes the impact of the three-phase system of soil. So when it comes to solid mechanics or fluid mechanics, we got only one unit weight or only one density parameter. We didn't have any adjective in front of density or unit weight. We only got one unit weight or density. So for unit weight, it is weight by volume. For density, it is mass by volume, both in solid mechanics as well as fluid mechanics. But in case of soil mechanics, we are having few adjectives in front of this unit weight or density term. Okay, so because of the presence, the heterogeneous nature of the substance. Okay, so first one will be bulk unit weight or bulk density, or it can otherwise called as simply unit weight or simply density. Okay, right. So gamma B, it is represented by gamma B. It is equal to weight divided by volume. So total weight divided by total volume. So total weight comprises of weight of solids, weight of water, and weight of air. We already spoke about that. Weight of air, it will be taken as 0. It is neglected during calculations because of its very feeble contribution to the weight. We are neglecting it. But in case of volume, we have to take the volume of air into account. So total volume, it will be equal to volume of solids, volume of water, and volume of air. Okay, so this is the split up of weight and volume terms, right? Similar, we can represent the same in densities also. So bulk density, it will be equal to total mass divided by total volume. So we can split up these terms in a similar fashion as we did earlier. So the total mass, it can be written as ms plus mw, meaning mass of solids plus mass of water. Similarly, in denominator, the total volume can be split up into volume of solids, volume of water, and volume of air as three terms. Okay, so you have to put your practical thinking while writing the equations also. Okay, Then only you can know the difference why we are not using weight of air, but we are using the volume of air. Okay, why weight of air is not considered, but volume of air is considered. You have to know the difference. Okay, so think in a practical way, then you can easily understand it. Okay, so and the next point is a common conversion relation. Okay, so to find out unit weight from density, you have to simply multiply with the acceleration due to gravity. Okay, so gamma is equal to rho into g. It is a very simple conversion. You could have studied in engineering mechanics itself. Okay, so the next unit weight is dry unit weight. Okay, so first one is bulk, in which we considered as a whole, total weight, total volume. Dry unit weight, let's see what is the difference from the bulk. So dry unit weight or dry density, it is represented by the letters gamma d. Okay, which is equal to Ws divided by V. Means in numerator you can see the change, in denominator there is no change. So in numerator, instead of total weight, okay, we are using only the weight of solids here. We are not taking the weight of water into consideration here. Okay, so you can see the difference clearly. So in bulk, we took the weight of water into consideration, but in dry calculation of dry unit weight, we are taking only weight of solids. The weight of water is not taken into account. Okay, denominator no change, total volume. Okay, so gamma d, dry unit weight is equal to weight of solids divided by total volume. In similar fashion, we can write the dry density also. So rho d is equal to mass of solids divided by total volume. Mass of water is not taken into consideration here. Right. So this is the difference between bulk and dry. Okay. So the third one will be saturated unit weight or saturated density. Okay. So let's see what is the difference here. So this is a special case of bulk density or bulk unit weight. Okay, so what that specialty means, when we measure the bulk unit weight of the soil in its fully saturated condition, then it is called as saturated unit weight. That's all, nothing changed. Okay, so exactly we have to write this formula like this. Okay, I'll show you write the formula again. So if you want to write the saturated unit weight in a precise manner, you have to write like this. So gamma sat is equal to total weight at saturated condition, fully saturated condition. So if you want to write the equation for a saturated unit weight precisely, this is the manner you have to write. Okay, you have to add a bracket. Okay. So means the total weight at a saturation condition. Okay, so that is the meaning of this. Okay, because there is no term like this W sat. There is, we haven't seen a term like this in our three-phase diagram. You can see that again. Look at this three-phase diagram. We only got total weight capital W, Ws weight of solid, weight of water capital WW, and weight of air capital WA. There is no such term as W sat and all. Okay. So here in precise, you have to write like this only. W, put it in bracket, and suffix you can write saturation. Okay, it means the total weight of the soil mass in its saturated condition. That's all. Okay, right. In similar fashion, you can find the density also. Instead of weight, you have to put mass. Again, you have to include the mass in brackets. Okay, mass of the soil at its saturated, fully saturated condition divided by total volume. If we calculate the weight or mass at the saturated condition and divided by the total volume, we will get the saturated unit or saturated density respectively. So this is the meaning of it. The next unit weight will be submerged unit weight or buoyant unit weight, or the other term for this is effective. This property can otherwise be called as effective unit weight also. Effective unit weight also. Okay. So as I already said, in soil mechanics, for a single property, there may be many names. Okay. So for this particular property, submerged unit weight, it got two alternative names. One is buoyant unit weight, and the other one is effective unit weight. Okay. So this single property can be called by these three names. Okay. Either submerged unit weight or buoyant unit weight or effective unit weight. So what is this means? So submerged unit weight, it is the weight or the unit weight of the soil in its submerged state. Okay, so the difference between saturation and submergence means submergence is, so in saturation the level of water will be at the level of the soil mass, but in submerged condition the level of water will be much higher than the level of the soil mass. Means the soil mass is submerged below a column of water. Okay, so that is called a submerged condition. Okay, so if you calculate the weight of the soil mass in its submerged condition, then unit weight of the soil mass, then it is called as submerged unit weight. Okay, so how mathematically we have to find this means, so gamma sub, it is represented by gamma sub or gamma dash. Okay, gamma dash or gamma sub both represents this property only, submerged unit weight or buoyant unit weight or effective unit weight only, both. You can use both alternatively, nothing wrong in that. So gamma dash or gamma sub, it can be calculated from the saturated unit weight of the soil. Okay, so if we subtract the saturated unit weight with the unit weight of water, we will get the submerged unit weight of the soil. Okay, so the submerged unit weight is roughly one half of the saturated unit weight. It is roughly, not exactly, please keep that in mind. So roughly it is one half of the saturated unit weight. The reason being, we know the unit weight of water as how much per? Hope you know it. So what is the unit weight of water? Okay, I will tell it. So the unit weight of water is 9.81 kilonewton per meter cube. So if we take the saturated unit weight of any soil, for instance, it will be roughly in the range of 18.5 to 20, 21 and out. That's it. Okay, not more than that. 18.5 or 18, say 18 to 20 or 20.5, in that range only. Okay, so if you subtract 9.81 from the saturated unit weight, we will get approximately half of the answer. Okay, so that is why we are giving the statement here. The submerged unit weight is roughly one half of the saturated unit weight. Okay, because in general, the saturated unit weight of soil is twice the unit weight of water. You can say in other words like this also. Okay, please keep that in mind. The saturated unit weight of soil is roughly twice the unit weight of water. Okay, so please keep that in mind. Right. So the next last unit weight property is unit weight or density of solids. So far we were discussing the unit weight of soil, okay, a mass material. But this particular property, we are talking about the solid portion only, not the entire mass. See the difference carefully. So far, last four properties we were discussing for the soil mass entirely. But this particular property, we are discussing the solid portion only, the solid portion present in the soil only. We are taking that only into the consideration. Okay, so it is represented by the letter gamma S, and it is equal to Ws divided by Vs. So far in all the three properties, the denominator was total volume, but in this particular property, the denominator is changed into volume of solids. Instead of V, we are writing Vs here. Okay, so please see the difference. Right. Okay. The next one, very important property, the specific gravity of solids. Specific gravity, this particular property you could have studied in your fluid mechanics already. Okay, so specific gravity denoted by the letter G in soil mechanics. But in fluid mechanics, we will use the letter capital S for denoting the specific gravity. Hope you remember that. But in case of soil mechanics, we are using the letter capital G for specific gravity, because we have already designated the capital letter S for what property? Degree of saturation. Okay, so for degree of saturation, we have already designated the letter capital S, and hence we are not using that again here for mentioning specific gravity. Okay, so instead of that, we are using capital G here. In some times or in some textbooks, they will be written as GS. Okay, specific gravity will be mentioned as GS in some textbooks, or even in your question paper, maybe they will be giving specific gravity in GS. Okay, don't think it is some new term or special specific gravity or like that. Okay, G or GS both denotes specific gravity only. Okay, right. So it is defined as the ratio of the unit weight of solids to the unit weight of water. Okay, so the definition is the ratio of unit weight of solids to the unit weight of water. In fluid mechanics, we could have studied the definition already. So there we were using the term the ratio of any fluid divided by any fluid to the standard fluid. You could have studied that in fluid mechanics, but here we definitely know it is the ratio of the unit weight of solids to the unit weight of water. Okay, so the standard reporting temperature of specific gravity is 4 degrees Celsius. So you may get this question in exam, though this is not up to the gate standard. You could expect this kind of questions in our state service exams. Okay, state engineering service exams. You can expect this kind of questions. The standard temperature or finding a specific gravity, standard temperature for reporting permeability and all. Okay, so you can get this type of simple questions in state service engineering services exams, but for this is not a gate standard question, but nothing wrong. Okay, please keep that in mind. The reporting temperature for specific gravity is 4 degree Celsius. Okay, right. Okay, so the unit weight of water can be taken as 9.81 kg per meter cube, that I already told in the previous, while discussing the previous property itself. So 9.81 kg per meter cube. So specific gravities of solids is numerically equal to the ratio of the density of solids to the that of water. Okay, so in this case, density of water can be taken as 1 gram per cc. So we are having two alternative or two different methods for finding the specific gravity. One is using the unit weight terms, and another one is by using the density terms. So either you can find out using the unit weight properties you have in your hand, or you can use the density properties. If you have a density in your hand, then you can use the density property for finding the specific gravity. Okay, right. So one thing you have to keep in mind is when you are using the unit weight in numerator, then you have to substitute 9.81 in denominator. If you are using kilogram or gram in numerator, then you have to substitute the corresponding density value in the denominator. If you are using, say for example, if you are using kg, if you are going to substitute the density of solid grains in kilogram in numerator, then you have to write the density of water in kilogram in denominator. What is the density of water? Density of water, 1000. It is 1000 kg per meter cube. If you are going to substitute the density in grams, means then you have to write 1 in denominator, 1 gram per cc. Okay, so 1 gram per cc. So here cc denotes centimeter cube. Okay, right. The next one, some interrelationships. Okay, so the relationship between weight of solids, total weight, and the water content, ws, w, and small w. Okay, so these interrelationships will be very helpful while solving problems. So the first interrelationship is So the first relationship is Ws is equal to capital W divided by 1 plus small w. Okay, so if you are having total weight in your hand and water content, so then you can find out the weight of solids in this manner. Okay, alternatively, you can find the total weight. Alternatively, you can find the total weight from weight of solids and moist content like this also. Alternatively, you can find out the total weight like this. So by means of rewriting this equation, Ws into 1 plus W. Okay, right. Next, the relationship between void ratio and porosity, very important one. So N is equal to E divided by 1 plus E, or alternatively, E is equal to N divided by 1 minus N. There are derivations for this relationships, how we arrived this particular relationships, but we need not waste our time by discussing those derivations. You can have studied that in your academics itself. So let's move to the core points alone. Okay, let's move to the core points alone. Okay, right. So next derivation, next relationship will be between E, W, G, and S. That is void ratio, water content, specific gravity, and degree of saturation. So E is equal to WG divided by S. Okay. So alternatively, this can be written as S E is equal to W into G. So you can remember this equation like sewage. Se is equal to Wg. You can this is a hint only, so you can remember this relationship like that. Sewage, Se is equal to Wg. Right. The next relationship will be between gamma b, writing gamma b in terms of G, E, S, and gamma W. So this is the equation. Gamma b is equal to gamma W into G plus Wg divided by 1 plus E. Okay, right. So for dry unit weight, we have to substitute uh, S value as 0. We already discussed that for dry soil, the degree of saturation is 0. If we substitute the value of S as 0 in this particular equation, we will get the relationship for dry unit weight. So if we substitute 0 here, we will get G into gamma W in numerator, and in denominator, no change, 1 plus E. Okay, so this is how you have to arrive dry unit weight terminology. Similarly, for saturated unit weight, we have to substitute the value of S as 1 in first equation. Then we will get gamma sat as G plus E into gamma W divided by 1 plus E, like this. So this is another relationship between submerged unit weight. Okay, so gamma sub is equal to G minus 1 into gamma W divided by 1 plus E. And the last one will be dry unit weight and GW and percentage air voids. So 1 minus Na G into gamma W divided by 1 plus Wg. This particular formula, that this last one, this equation will be helpful in compaction property. Okay, there is a line called zero air voids line. So for drawing this line, this particular formula will be useful. We'll discuss about that in later. So let's take a example problem. A wet sample weighing 23 Newton had a volume of 1150 centimeter cube. After oven drying, its weight is reduced to 19.6. From where? So initially its weight was 23 Newtons. After oven drying means keeping that sample in hot air oven for 24 hours at the temperature of more than 105. Okay. right? So that is called as oven drying. After oven drying, its weight is reduced to 19.6 newtons. The specific gravity of solids was found to be 2.65. So these are the given data. So totally we have four data given. So one is wet weight of the sample, second one is dry weight of the sample, third one is volume of the sample, and the fourth one is specific gravity of the sample. These are the four data given in the question, and we are asked to find the water content, bulk unit weight, dry unit weight, saturated unit weight, effective unit weight, void ratio, porosity, and degree of saturation. So total 8 parameters. So with this 4 parameters, we have to find 8 parameters. Okay. So again, I have to remind that this is not a particular gate type of question, but in gate exam, you may be asked to find any one property or sometimes two properties. Okay. So they will be giving they will be giving the given data in the same fashion. Okay, so 4 or 5 given data, and you are supposed to calculate or supposed to find out one or two properties from the given data. Okay, so for example, I'm taking all the properties in one question itself. Okay, don't think you will get this big question in gate. Okay, but you will be asked to find any one or two property from this list. Okay, so please keep that in mind. Okay, so writing down the given data. So the total weight, that is a wet weight. Okay, wet sample means it contains the weight of water and the weight of solids both. Okay, so both comprised the weight of sample is 23 newtons. So after oven drying, what happens? The water gets removed. Okay. Okay. After oven drying, the water gets removed by means of evaporation. Okay. So which means the 19.6 here denotes the weight of the solids. Okay. So initially, weight of solids plus weight of water is equal to 23 newtons. That is the total weight. After oven drying, from that mixture, the water is removed. Only solids is present now. Okay, after drying, only solids is present now. So hence, we are writing Ws as 19.6 newtons. The third data is 1150 centimeter cube. That is the volume. And the last data is specific gravity was given. It is 2.65. Now let's find the asked properties one by one. So for water content or moisture content, the formula is small w is equal to WW divided by WS into 100%. So we are writing, substituting the values here. So for finding out water, weight of water, what we can do, we know the relationship. Total weight is equal to weight of water plus weight of solid, right? So the total weight of a soil mass is contributed by only by these two things. Weight of air is not taken into consideration, so it has very feeble contribution in that. So we are not taking that into consideration. So this total weight is contributed only by these two. So this is the equation. So now we need WW here. In given data, we got capital W and WS. So by means of rewriting, we can find out the weight of water, WW. Okay, so WW is equal to capital W minus WS. We can write that manner. Okay, so from right hand side, we are taking the WS to the left hand side. So the equation becomes W minus WS is equal to WW. Okay, so that is what happened here. So 23 minus 19.6 means capital W minus WS, which is equal to the WW. Okay, weight of water. Okay. In denominator, we got only the weight of solids, and the value is already we know 19.6 given in the question. So substituting the values, we are getting the answer water content as 17.35 percentage. Okay, so 17.35 percentage is the answer we got for the given sample. So the next property is bulk unit weight. So what is the formula? So gamma B is equal to total weight by volume, and substituting the corresponding values. So total weight is given in newtons. So we are substituting that in kilonewtons. So in order to get the final answer in kilonewton per meter cube term, so we are doing these things. So 23 Newton. So for converting it to kilonewton, we have to multiply it by 10 power minus 3 because 1 kilonewton equal to 1000 newtons. So rewriting 1 newton is equal to 10 power minus 3 kilonewton. Okay, right. So 23 into 10 power minus 3 divided by the total volume is 1150 centimeter cube, given in centimeter cube. So we are converting it into meter cube. So for 1 um, meter, we got 100 centimeters. So in other words, 1 centimeter equal to 10 power minus 2 meters. So here we got the cube format of that unit. So we are taking 10 power minus 6, 10 power minus 2, 10 power minus 2, 10 power minus 2. So 10 power minus 6. Okay, right. So substituting the values, we are getting the answer as 20 kilonewton per meter cube as bulk unit weight of the soil. Okay. So the physical meaning of this is, if we dump 1 meter cube box with this particular soil, its weight will be 20 newtons. So that is the physical meaning of unit weight. So if we dump 1 by 1 by 1 meter cube, that is 1 length, 1 breadth, 1 height dimensions cubical box with this soil, we will get, and weigh the setup, we will get the weight as 20 kilonewtons. That is the meaning of unit weight. Okay, right. Okay, next move on to the next one. Dry unit weight. So gamma d, it is equal to, we know the formula, ws divided by v. So 19.6 is the dry unit weight, weight of solids. So 19.6 into 10 power minus 3, for converting newton to kilonewton, 10 power minus 3 is added, divided by 1150 into 10 power minus 6. So we are getting the answer 17.04 kilonewton per meter cube. So alternatively, we can find the dry unit weight from the bulk unit weight relationship also, without using the original formula. By means of using the relationships, we can find out like this also. Okay, so that is given in the next step. Alternatively, gamma d can be find out by using gamma b divided by 1 plus w. You can find out gamma d in that way also. Okay, right. So next, for finding out void ratio, we are using this relationship, gamma d, g, gamma w, and e. We are rewriting this relationship in order to find out the value of e. Okay, so since the original formula for e is vv divided by vs, and we don't have both of them here. We got total volume, but we don't know how much of the total volume is occupied by voids and how much of the total volume is occupied by the solids. Okay, so and hence we cannot utilize the original formula of the void ratio here. Okay, so for that, we are going for the alternative method, that is by means of using the relationships, we are trying to find out the void ratio. So this is the simplest relationship from where we can find out the void ratio, because we can see the void ratio in various other formulas also. But why we are taking this particular formula for finding the void ratio means the number of variables is less in this one. So that is the reason. Okay, even in the bulk unit weight relationship, we have void ratio. Even in saturated, we have void ratio. But the reason for using the dry unit weight formula for finding the void ratio is the number of variables is less. That is the only reason. Okay, right. The number of variables is less, so hence our calculations can be simplified. So that is the reason. So now we are rewriting the formula. So E is equal to G gamma W divided by gamma D minus 1. Okay, so substituting the values, we are getting the void ratio as 0.526. So please note, take this. We are not writing void ratio in percentage, not like 52.6%. Okay, so please keep that in mind. Void ratio, it has to be expressed in numerals only. No percentage need to be calculated. Okay, not necessary. Okay. The next property, porosity. So for finding out porosity, the original formula is VV divided by capital V. We have capital V, total volume here, but we don't have the volume of voids. Okay, so again we are going to use the relationships. Okay, as we already calculated void ratio, we are using that this particular relationship, n is equal to E divided by 1 plus C. So from this we can find out the porosity value. Okay, so substituting the void ratio value in the relationship 0.526 divided by 1 plus 0.526, we are getting the porosity answer as 34.4 percentage. Similarly, the next, degree of saturation. So we know the original degree of saturation formula is volume of water divided by volume of voids. So we don't have that here in our given data, or we didn't calculate that anywhere in the previous steps. Neither volume of voids or total volume of water, we didn't calculate that in our previous steps also. And hence, again, we are going to use a relationship for finding out the degree of saturation also. So using the sewage relationship, S is equal to Wg divided by E. Okay, so substituting the known values here, we are getting the answer as 87.4. Now, please keep the note here. Water content is 17.35 percentage, but during calculation, we are substituting that in decimals, 0.1735. Okay, 17.35. We are substituting like this. Please keep that in mind. 0.1735 into 2.65 divided by 0.526. So we're getting the degree of saturation as 87.4 percentage. So the physical meaning of this is in the void's volume, 87.4 percentage is occupied by water. Remaining 12.6 percentage is occupied by air. Okay, so that is the physical meaning of this particular thing. Okay, so the next parameter is saturated unit weight. From the formula, G plus E into gamma W divided by 1 plus E, substituting all the known values, we are getting the answer as 20.42 kilonewton per meter cube. The last one, we are asked to find out the effective unit weight, or the other name for this is submerged unit weight or buoyant unit weight. All three represents the same parameter only. Effective, submerged, buoyant. All three represents the same properties only. Okay. So using the formula, gamma dash is equal to gamma sat minus gamma W. Substituting the values, we are getting the answer as 10.61. So one thing, or one bottom line we can draw from this problem is, we have found out, or we calculated 4 different unit weights in this particular one sum alone. Okay. We found out gamma bulk, that is bulk unit weight. We found out gamma dry. We calculated gamma sat. And we calculated gamma dash. We calculated all these unit weights in this one sum alone. Okay, let's arrange them in their ascending order. So if we arrange them in their ascending order, the effective unit weight is the least one. It got the value of 10.61. Comparing to all the other three, it got the least one. So gamma dash. Okay, so gamma dash, it is less than, what is the next least value? So saturated unit weight is 20.42, dry unit weight is 17.04, and bulk unit weight is 20. So the least of the remaining three is dry unit weight, gamma D, only 17.04. So that comes in the second place, second least place, gamma dry. The third one will be, the remaining two are, one is saturated unit weight 20.42, and the other one is bulk unit weight, which is 20. So the third least is bulk, gamma B. And the last remaining one is gamma sat. So the bottom line we are drawing from this particular sum is, for a same soil, it attains its maximum weight in its saturated condition. Okay, gamma sat. Okay, a soil in its saturated condition will be much heavier. Okay, so the same soil will be lighter in its buoyant state or submerged state. So that is the bottom line we are drawing from this uh, particular relation. Okay, for a same soil, if it is in a submerged condition, its weight will be very less. If it's in a saturated condition, it will be more. Okay, when it comes to dry and bulk, in its dry state, its weight is less compared to its bulk state. Okay, because in dry state only air occupies the void spaces, but in bulk state, uh, water occupies a part of the void space, and hence it is heavier in its bulk state. Okay, so that's all for today's session. We can discuss the remaining problems in our next class. If you have any doubt, please ask now.
Sir, thank you so much for the class, sir. Can you share this PPT to the group, sir? To the
Sure, sure,
participants, sir.
sure.
Okay, sir. Thank you.
Sure, I will share the PPT, and also I have some worksheet problems also. Okay, questions. Okay, previous gate questions in this topics. I will share that also.
Thank you, sir.
Thank you.
Students, if you have any queries, any relevant materials needed, means kindly share in our class WhatsApp group. I will post in this same content to concerned faculties. Okay, I will collect some materials for you and prepare for the examination. That's all. Okay. Bilal sir, thank you for
Thank you,
your
sir.
wonderful session. So we will
Thank
meet
you,
in
sir.
the next week, sir.
Okay, sir. Sure. Thank you,
And
sir.
also share the material to me, sir. I will post in the class group.
Okay, sir. Sure, sir.
Thank you, sir.
Thank
Thank
you,
you.
sir.
Thank you,
Thank you, sir.
students. All of you can leave.